and I really like the shape it's taking, but I think this is going to need some heavy testing. Now I'm missing just, I think, a let me see. I'm missing, I think, just a couple things. I'm missing two things. These two things in here for the splitting, and then I'm missing the simplification part in here. Am I? Oh, yeah, that's a thing to merge the edges that are uh, uh, identical. Okay, so that's missing actually. But I've done most of the stuff, and so and what I have to do, what I want to do is I want to yeah, basically change the initialization as well and think about the naming as well. Hypergraph, not hypergraph, and stuff like that. That's still gonna take a while until we get that in good shape. But first, I really want to run all these corners and oh, I still copy edge is missing. Okay, cool. So what do we do? What do we do? What do we do? What do we do? So let's finish up the splitting states thing. I'm not just coding and not actually testing anything. That's really not good practice. It's all probably just not working at all. But I'm happy because I feel I finally kind of have found a bit of the sort of the actual structure that I want the tool to have, right? So the splitting was to just basically say if a node is not in the 0 or the 1 state, and that's something that'll have to be generalized for like higher dimensions, then we split these into, so we copy the edge and then we copy the edge and yeah. So we basically put one in the cat 0 and one in the cat 1. And my guess is that I kind of have to take the that's the tricky part, right? That's the tricky part. No, it should be all. So what do I do with the weight now, right? I probably need to get the coefficient. So I probably need to get the coefficient of 0. So I need to get like the coefficient for 0, the coefficient for 1. So basically kind of say, um, these, I think that's the way you do these. Get 0 and then, you know, and this is for the get 1. And so I think that this is good enough, but what I then need to do is I need to take a look at the edge ID, right? And just say self edges EID weight. I never know if it's like these or like these, kind of. So, because here's where we keep the 0 coefficient, and here's where we keep the 1 coefficient. That's just whatever. This is just random decision. I could just do it otherwise. I just could do it, the other way around as well. So that's not an issue. And hmm. What else? What else are we doing? So I think that's about it because we're just giving the 0 and the 1 here. So let's do the copy. How is the copy? So I have an edge and I want to copy the edge. So I think what I just do is I basically, now the question is, do I copy the weight? I think so, right? So I just basically say, good. Copy edge is basically a hyper edge with amplitude, weight, sorry, self edges, edge ID weight, and yeah, and basically I think one thing that I'm not doing is HyperEdge. It's just no IDs. I think I uh, add edge or something. Like, how do I know? How do I think I think I'm adding sometimes. I'm creating edges, but I'm not really adding them to the hypergraph. So you know you know what I mean. Like, but anyway, so I have these, and then what I should do is what is the move? Yes, it's basically the same like move node to edge, but without the popping, right? So, oh no, it's a copy. So what I should do is for n in uh, self edges edge UID, I get basically the node is self nodes n, and what I do is I just do new node is basically node, and I think this is just I just give it the qubit, so node qubit, and then I just say new node state equals end state node state. So I'm copying the node, and then I'm I definitely need to add self edges copy UID is the copy edge. So I add these to the edges, and then I say, you know, basically self edges. How am I doing this here? Initialize. Okay, no. Edges. What am I doing? So now what I'm saying is I'm doing self add node to edge, and what comes first, the node and then the edge. So new node UID and copy UID. So I'm adding the node to the edge, right? Is it all that we need to do? So create the hyper edge, add it to the edges, and then iterate over each node, make a copy of the node, and then add the node to. Yeah, I think that is basically it. Oh, and oh, I've done this already here with the right weight. Okay, cool. So that's copy edges. Would I have any other to-dos open other than this? To do. Yeah, I think check for error, it's true. Check for error, it's true. Text resolution shouldn't match anymore if the edge has been touched previously. I don't know what it means, so I'm just gonna forget about it. Um, okay, that's an obvious to-do that I'm not gonna have in here. I'm gonna delete these for the moment because I'm gonna change the signature of these. But okay, so we have that stuff. Good. What about these? Simplify. I can only have like so all the cubes are composed, and now what I need to check is whether the two the edges are completely the same. I think I can just reuse the code that it was in the decomposition, because in the decomposition I'm checking can decompose, and can decompose is basically checking if I think I can use can decompose code. What's more, but okay, I'll copy that because maybe I will want to change the logic later. So I'll basically say, you know, can I simplify, right? And can simplify edges. It just means basically that edge. And actually, simplify qubits should be the same here than decompose. So I just it's just basically this is what I'm doing. But here I don't need to do the recursive part because it's just I'm just eliminating duplicates. So I think it's just enough if I iterate over qubits. Oh, this is definitely missing something here. I think it was recursive. I needed. What's EID space to compose, right? EID space. What is this? I need to find the EIDs. That's something that I'm missing. That's something that I'm missing here. So, yeah. But I had done I think are composed. I think that has some good logic to reuse. Yeah, because it basically checks whether they're all in the same spot. And I should just have another method that basically uses the same, but it returns these actually. Or none. So so I would just say basically get edge IDs. Get edge IDs, right? Composed edges. I'll call it composed edges. So it returns the composed edges. Yeah, essentially. So actually, that part here is basically as easy as these equals self composed edges qubits. So, but actually, it doesn't have to be here. It can be after the composition. Otherwise, we don't really care. And and I was now, where was I? I was doing the simplification. What? Simplify. I know I'm probably just going too fast, and if you're not, like, if you're haven't been following, it's just confusing, but I really promise that at some point I'll just do a bit of a deep dive into the actual code and, kind of do a bit of a hands-on demo. It's just it's kind of the second rewrite, and I want to make sure that I get it right. So simplify. Can I simplify? So where was I? Are they composed? Simplify. So I have to check now whether whether I can simplify. So this is the same logic like here, right? Where I say cool. So I see if they're composed, right? What it means, what am I doing? What it means is that we can iterate over so we can iterate over these are basically self composed edges. Is that the way I called it finally? Composed edges, qubits, composed edges, qubits. So I'm getting the edges where they are composed in, and then iterating over all the possible pairs of these edges and checking, can I simplify the edges? If so, then the simplification is really easy, to be honest, because it means I can just drop one. I add the weight of the candidate edge. So the only thing that I really have to do here is, okay, so I probably should delete the edges later. I don't know, that's going to be problematic because I think we're going to have to use the recursivity because it just makes it easy. The recursive part makes it easy. So actually, let me just do the following. So what the simplification does is basically a copy. It's basically these, right? So simplify. So if I can simplify the edges, what I need to do is I just need to do basically. It's actually way simpler than that. I can just say, give me the target, right? And update the weight so it's the same weight plus, I think in this case it's a plus, because we're talking about the same set of qubits, and so that was a logic, right? So I add the weight and I just delete the source edge. That's it. Yeah, baby, that's it. That's what simplify edges does. And so what compose recursive, it's literally the same schema. So what the simplify recursive will do I think it's better if I take these because the composition was a bit trickier because I was playing with groups and whatnot. So here is I should take this one as an example and not this one. So decompose and simplify. So what the simplify does is okay. So if there's only one, then I'm done. Then it iterates over the stuff, right? And it says, can I look? Hey boy, can I simplify? Hey baby, yeah, please simplify. And so because I've simplified these two, what I want to do is I want to remove, and again, I'm simplifying to the, Yeah, here it's a bit confusing. So I'll use base and candidate as well. And so what I will do is I will merge in the base. So, and I'll delete the candidate. Um, to be honest, I should copy the edge and blah blah blah. Probably it's better, right? But let's keep it like that for now. So it simplify edges, base, and candidate, and so simplify base candidate qubits. And what I do is I only want to remove the candidate because the base one still should stay in the least as candidate to be merged farther down with other edges. Because remember, I'm just merging pairs, right? Um, cool. And so that calls and then simplify recursive again with the new updated stuff. And yeah, that's all good. And then and that's what the actual entry point looks like. They all have the same type of pattern. So it's a bit of a recursive trick with then checking whether a pair can be simplified, and then an actual simplification task. Then I update the IDs that are candidate, and so the set keeps keeps basically getting smaller to the point that once I do a run and I can't find a candidate, then it just returns the least, and then we're done. So this is simplify qubits. Recursion is such a powerful concept, man. Are composed, get the composed edges, and then basically simplify recursive. Boom, it's the same concept. It's really the same interface, which is nice. I mean, all these will be hidden, kind of, right? So only the simplified qubits is the one that's going to be public. Look, I think I'm done. Boom. Okay, now let's think about the initialization now. So the rewrite, check for error, check for error. Yeah. Yeah, we'll assume the user's cool. Yeah, I prefer to have less to-dos and then while I'll be testing, get a bit more. Okay, so let's think about the initialization, right? So we want to have two ways to initialize this. One thing is we want to have it so that I can initialize these just by providing the number of. And let's maybe already start here by saying, look, first is going to be the number of qubits. So I'm gonna keep that out. I know it's better practice to keep these things, but it's like first, let me just it just I know it's bad practice to remove these. I just want to make sure that I make up my mind on what I want here because the number of qubits is a must of qubits, and then I have to give it the dimensions, which by default will be 2 because will be then qubits, and then state vector. State vector will be there as a thing there, and then symbolic and a record gates. Just bothers me that it's here, so I'll just put it here. I know it doesn't matter. Good. Then I initialize these, initialize the labels, and then right. State vector. Yeah. Okay. I see what Jordan did here because I think Jordan was touching that. So record gates, gate log. So this is qubits now. and we're initializing always the node to 0, so raw. And maybe I should kind of give it a I'll have to figure out a better mechanism to keep track of unique IDs, but that's for later. To do better system for unique IDs. So if we have a state vector, right, then we need to initialize the stuff, and we're going to assume dimensions is 2 always. Yeah, because essentially what we would have to do here is kind of create hyper edges, right? So I would just basically say, and it's cool because I'm gonna assume that the state vector is an expression, so I'm gonna actually call it SV expression. So it's actually fuck that. If SV expression is not none, then what I do is I basically and here's why dimensionality comes into play, right? Because yeah, why not? Actually, let's do like that. So I know that the computational basis would be 2 to the power of the dimensions minus 1, right? In this case. So that's the number. And then what we're doing is basically, that's going to be easy. So for or while, kind of while, CB is bigger than 0, basically what you do is you do the coefficient is just the expression coefficient of SPQ ket CB, right? So now I have the coefficient. So now I have no. What am I doing? Yeah, I have the coefficient. And so each of these is a node. Remember, we have higher dimensionality. The problem will be that if we have 2 dimensions, wrong. So I need to combine these and that, obviously. That is just for one system, right? But here I still need to do, so I have 3 qubits, right? So basically, what I need to do is I need to do Q is basically NB qubits minus 1, right? And then I just, kind of go while CQ is bigger, while CQ is basically bigger equal than 0. And this is kind of now we're initializing each system, each qubit. So if I have, so if I have, say, dimensionality 2, right? Whoa, 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 whoa. But that's I'm getting confused. So you have, let's take the pain, let's take pain, let's take pain, pain. So if I have state vector that it looks like these, right? So I'm going to assume the state vector will be in the, why isn't that showing here? There you go. So if I'm going to assume that if we have, for example, we've got dimensionality 3, so this means we have the states 0, the states 1, and the state 2. With this, it means that each qubit can be in like 8 different states, right? Exactly. But now, on top of that, I say that I have 4 qubits. So now my wave function is going to have basically my wave function is going to basically have 2 to the power of 4, right? So 6, is it correct? Because basically, man, I'm feeling stupid. Right now, I'm feeling really stupid. So what if I have, no, that's stupid. If I have 5, if I have, say, 2 qubits, I have basically a 2 to the power of 2 wave function because I need to define these computational basis elements. Yeah, exactly. If I have 3 qubits, it's 2 to the power of, 2 to the power of 3, right? But this is because yeah, okay. So if I dimensionality 3, it's 3 to the power of 2. So that's the idea, right? Yeah, right? So it's be 6 elements because basically I can it's like 0 0 0 1 0 2, right? 1 0 1 1 1 2, and then 2 0 2 1 2 2. It's 9, sorry. What did I say? Yeah, yeah. So it's dimensionality to the power of qubits. Yeah, dimensionality to the power of qubits. Um, dimensionality to the power of qubits. So this is the amount of elements that I have to process. So what? So uh, so state vector size is basically, what did I say? Dimensionality. So these, no, these dimensionality time to the power of um, qubits. Exactly. Yeah. And so how can I process that though? Uh, I guess what I need to do from an expression perspective, right? Um, I guess I can tell the expression to be, something like ket0 times ket1 times ket2, like that would be 1, right? But I can also just be using strings, right? And say, these ket. Yeah. Uh, exactly. So Yeah, well, that essentially is a number in base uh, d as the 4 dimensions. Yeah. So the only thing that I need to do is um, iterate, get the number in that basis, and then I know what are the qubit states, right? So I need to basically, how can I do that in there's a lot of Python trickery involved in here, I guess. So I need to essentially, so um, I equals 0, and then while I is smaller than the SV size, um, so the I basis, this would be, this is like change to base dimensions. Then I basically then get the coefficient, right? So then you get like SV expression, coefficient of I base, right? So that will give me the coefficient that I want because that's the weight of the hyperedge. And then create nodes out of each digit in IBase, and then basically create the edge. So and then with the edge, create the edge, and the edge will be basically just hyperedge, and I give it the weight, which is basically the coefficient. And then, well, that I probably should do before. So I create the edge. Oh God. I create that, and then what I do is, yeah. So how do I do that? So let me open quickly. Chrome, Python. So Python, change base. Oh, there you go. An integer to string in any base. Oh, okay, cool. I guess we can just copy paste that. And I will try to understand that, okay? So it's just that. Yeah. So I'll do it in, just will be in the utils, I guess. I mean, I don't know if this is going to be in utils or if this is going to be, it's not part of the, that's cool because it will allow me to do also hexadecimal base, like by using the actual X base. That's cool. So this should definitely not be part of that, but should rather be part of this. So there's this import in here to take care of, and then there's this whole okay. So what we're doing is we're now doing the IBase, And then the base we said is dimensions, right? Dimensions, we'll just call it D. Yeah. And then because we know the amount of qubits, then we know how long the string is, right? So actually the node creation is basically, we know qubits, right? So j equals 0, and so we can just say it's like while j is smaller than nb qubits, so it's an nb qubits, right? Basically, node is just a node, right? For qubit, so this is q plus j, right? And then we say node state is basically the coefficient. It's basically the coefficient times ket. And now I base j. So that's the digit in that string. That's that specific qubit has that state, is in that state exactly. And now I'll say self add node to edge, and I say n UID, and the edge is basically UID. So for each element in the state vector, I'm creating an edge, and then for each digit in the correct base, I'm creating a node, and this node qubit labels. I should actually append this qubit label, and then for each node, yeah, and then I'm just doing j++, and then also here I'm doing I plus 1, right? So that seems about it. That will definitely have to be extensively tested, but I think that's what it's doing. So I think that's correct. So it kind of reads, it reads each element, and then out of the string in each element. So the assumption here will be expression is in format like, you know, yeah, exactly. That's cool. Awesome. I think I'll leave it here. I mean, I'm getting there where I can start to, soon test stuff properly, but I'm happy that at least I got to do this one here, because now it's also going to be the basis for the QD thing, right? The dimensionality. And maybe, I mean, what are, yeah, I think that's really it, is it? To do, yeah, okay, cool, this law stuff. Yeah, that's it, really. Well, I would have to steal, yeah, I would have to steal now, basically adapt the parts of the code where I use ket0, which is basically everywhere. But that's going to be the next step, right? So I'm gonna, because this is going to have to be then generalized. Yeah, it's going to have to be generalized. Because when we'll do splitting, for example, we'll be splitting like across multiple. So we're actually doing, splitting 3, 4, 5. If you've got like a 3-dimension system, right, like a Q-tree, then we might have to create 3 edges, one for each computational basis. So this definitely then becomes, okay, what's wrong here? Something's wrong. What is the? Have I just missed something with the way? So we define that, and then if else, we do another for. Where's the problem here? Why is this in red? Like as if these would be somehow, I don't know. Oh, maybe. I don't know, that's just that we've removed something. Maybe that's the same. Yeah, okay, but this is it. So and at least that kind of marks the beginning of the multidimensionality, and we'll. So I guess what I'm gonna do in the next stream is get 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 there, get to test stuff. I mean, you know, we can actually do just a quick check. Uh, no, big book. I hope it has zero fill. Oh crap, that's sign as well. I don't want signs. I hope it has zero fill. um, anyway, is this working or not? There's an error somewhere. Boom, boom. So I like that we can initialize with actual expressions because we can also initialize with symbolic expressions, you know? Oh, wow. Yeah, we can actually initialize with symbolic expressions. I never thought about these. That's pretty cool. That's pretty cool. Let's just delete everything, all the different tests that we had here, and let's start with a clean, or maybe let's start with a clean notebook. You know what? It's fine, we can keep this one. What for to keep all stuff? What I mean is, you know, we'll start with just these. So first of all, cell or edit, delete cell, edit. I can just do this. Yeah, I like that. Awesome. So there we go. And you know, I'm assuming it's gonna break because like I've done shit. Like I haven't tested anything, so I'm sure I missed somewhere a an indent or something like this. And yeah, an indented block. Line 322. 322. That's here. That's the problem is here. That's what it tells me. 322. Ah, okay, there we go. What have I done? Why do I have another? Okay, cool. Start clear output. It's going against law. I don't know why. Still like, oh, look at these. This is a problem. This is a big problem. And maybe that was the whole thing with the returning here. Let's do another run. It's still complaining though. What is wrong with these? What am I missing? It's well indented. Everything is well indented. Split qubit state. Yeah, everything is well indented. We'll see. But I'm thinking I'm going to leave it here. It's time to. Oh, okay, cool. So it did not. It did not fail. Symbolic false, and so what was the printing stuff? Just print row. So we're just going to do these print row system. So just testing. That's going to be the first things that we're just going to be testing. We're going to do this incrementally. Yeah, now I see here. There's still a number of qubits left somewhere in here. Qubits. Which again, that is not, so that actually still, I know, that's okay. It creates the labels. Cool. Yeah. I don't know why it's so slow. Anyway, this is not defined. It's these. There we go. And what if I give it a state vector? I'm really curious. So SV expression, right? What if I just say, look at the SV expression, my friend is, for example, SPQ cat 3, right? Or cat 0. Let's just do this. Before assignment. Integer, that's I, not I base. Obviously. Okay, I keep saying that's the last time I test, but I should probably just stop. Let's see what happens. Well, I should break because that should definitely break. Yeah, okay. Okay. It's like, come on. Okay, but I was already here, so last time. I promise it's last time, and I'll stop this. Oh God. I should have known. I should have known. That's so bad. Now it's the last time. I promise. I just want to know if at least the most basic use case works at all. Um, but it's just being so slow on the notebook that it just bothers me. I feel I'm just like staring at these, man. Come on. Yeah. But basically, that would be the idea. So, you know, come on, activate the environment. Git add git commit final touches plus init dimensionality. Yeah. Git push. Please, 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 the most basic stuff. Why is it so slow? Again. Yeah, whatever. Fuck. Yeah, it's just the whatever. I'm done. I'll keep testing in the next session, which won't be far away from today, but that was a good one. So basically, we kind of completed that stuff. This red stuff bothers me a lot right now. Oh God, but there's something fucking missing here somewhere that just makes that linting. I don't know what is it. I don't know what is it. It's just something for. No. Okay, there you go. There's no change, right? Yeah, okay, cool, perfect. Whatever. Goodbye. See you next time.